good. Well, I was going to say good evening, everyone. It's 9 o'clock in the evening here in the UK. I guess for most of you, it's kind of mid to later afternoon, or even earlier in the afternoon, depending on whereabouts you are. Great to be with you. So just to give you a little bit of a view of where I am, this is a little picture of the UK. So I'm down there on the bottom right-hand side in the bit that's sticking out, which we call East Anglia, and I'm actually in a coastal town called Felixstowe, so about a mile from the ocean here. So that's great. So it's great to be joining you wherever you are across the US or beyond, I guess. So to compress or not to compress, that is the question for this evening. And specifically, I wanted to talk about distributed production. So what I think we would have a few years ago classically have called contribution circuits. But it's all about, as we start to mesh the way we actually do program production, I encompass this with the term distributed production, and we'll say more about that in a minute. Just two very quick slides about Nevion, just in case you're not familiar with everything that we're doing. First of all, we are very passionate about open standards. As Bob's already said, I'm very involved in a lot of the standards bodies, as is Luan and several of the other Nevion team from across the globe. And we have a passion that everything that we do is open and is standards based. So that's kind of part of the DNA that Nevion is. And in case you're not familiar, we have kind of two main product areas that aid our total solution space. One is Video iPath, which is a total orchestration, SDN control and monitoring solution, pure software proposition. And then Virtuoso, which is a software-defined media node, which has upwards of 30 different media images that you can actually load to do various processing functions for both video and audio throughout the production chain. We're proud to have been involved in all of the standards testing and qualification programs that have been running over the last few years. And last but not least, we produce this book, which we update twice yearly. I was going to say at the trade shows, but of course, that's kind of, what are they? I do vaguely remember them. But we update it twice a year. It's called From Baseband to IP to Virtualization. And we are about to publish in the next couple of weeks a new electronic version of the 10th edition of that. So we try to make it as up to date. It's got all the background about standards, where they are, as well as kind of the emerging technologies and how the industry is shifting. So if you'd like a copy of that, then do reach out to me. My email address will be elsewhere in the presentation at the end, but also you can find me online on LinkedIn or whatever. It'd be great to share that with you if you're interested. Okay, moving on. So we're looking at compression. And as I start to think about compression and we look back about the last 80 years of television broadcasting, I guess interlace was probably one of the cleverest, earliest inventions of compression. You know, how can you keep that frame rate up, but actually keep within a certain bandwidth? And the idea is, you know, you send half the frame, one field at one point, and then you send the other half of the field, gives the perception of a higher frame rate, whilst only sending half the information for each field. So very ingenious. Unfortunately, just like all of these elements of ingenuity from times past, we live with the legacy of interlace still in several environments, which is a bit frustrating, especially as it comes when it comes to some elements of more modern compression technology. Interlace is a bit of a bane, but I know over in the US, you guys are stuck with the partial frame rate, so I'm not going to wax about anything else on that one. And just thinking about contribution, this is a diagram that I grabbed. This is a BBC drawing from many years ago, although I did notice actually it was updated in 1990, only 30 years ago. But this is the BBC TV entire contribution network across London. It was all on coax, switched coax by relays in the various telephone exchanges across London. So that was all in standard definition, compressed, interlaced video. Anyway, so those two flash from the past. So moving on. So the context of what I'm trying to cover today is distributed production, and as I've kind of already alluded to, what we're seeing now is, you know, IP facilities interconnected to other IP facilities into IP remote production environments, like OB vans, etc. And we need to bring those all things together. So holistically, that whole title I call distributed production. And Obviously, within that environment, there is potentially the requirement for compression, and I'm going to unpack that a little bit more before we get to the compression in detail. What I've now added onto this diagram, as you'll see at the top, is the cloud, because the cloud is actually becoming ever important as a part of the production ecosystem. You know, that's where we're all heading towards, I guess, for a fair proportion of where all of the data processing is going to be located as the kind of end game of the architecture of distributed production. And obviously, again, compression actually is a key and a relevant element in terms of going to the cloud and from the cloud as well. So again, I'll unpack that a little bit later as we go. Now, scalability is a key element. One of the things we're seeing with scale at the moment is just the sheer number of connections in facilities. We have, in recent deployments in the last 12 months, gone in excess of 100,000 media connections within a facility. Now, admittedly, in a 2110 Essence world, you're actually handling several signals where for every one of those ones that you would have had on an SDI router. But even so, like over 100,000 connections is a crazy number of flows to be actually looking at. But also, obviously, in terms of scalability, it's not just the number of connections, but again, thinking of compression, it's both the increase in temporal and spatial dimensions of the video itself, going to UHD, going to ultra high frame rate as well. So, you know, if we go to 120 frames per second of a UHD flow, and then suddenly we've got a lot of significant extra requirements for bandwidth and therefore potentially for compression. So IP benefit. As we started to roll out the original, I guess, the first handful of IP studios, maybe 5 years ago now, I think, you know, some people were possibly arguably rightly pointing out that it was little more than a substituting of an SDI signal with an IP flow equating to that signal on a piece of fiber instead. And you know, doing it just like that is at best probably a cost neutral exercise, because you know, you're not really achieving anything. But this slide to me is the key thing about what we're aiming to do, because with this whole distributed production, now we're doing IP in the wide area connectivity as well as within the facility. Then suddenly we're able to actually share real estate resources, so we can share studio floors between locations, we can share galleries, we can actually share processing resources. So all of the processing stuff that you maybe use, be they replay servers, be they, you know, whatever stuff that you need to actually make the production, those resources can be shared as well. And then most importantly of all, we can share people, because we become geographically agnostic, if you like, in the way we do it, and therefore we can actually make the best use of our people resources as well. So those for me are the three key tenets of IP benefit, if you see what I mean, which is so much more than just replacing the SDI with IP. So a couple of quick examples of that. This is a pan-European network which we've been involved in deploying, some of which has now gone live. And again, the concept here was to have two good data centers that you can see there on the left, and then have multiple users in many countries across Europe actually making use of all of the processing resource in those two good data centers. So to me, this is actually one of the best examples that we've been involved in to date of distributed production. And very specifically, we're going to come back to it because the international connectivity between the countries all are using compression. And I'll talk about that in a little bit later on. Just before we get there, I just want to look a bit further ahead. Some of you that will see me present will have seen me present this slide in the last couple of years, because for me, this is the kind of the end game, really. We're at the moment, we're in this world where we've still got our raster legacy of, you know, scanned video and the way we present, the way we handle the data. 2110 is still largely speaking analogous to, you know, the linear raster delivery that we've been loving for the last 80 years. But actually, we don't need to work like that moving forward. And indeed, within 2110, we've tried to make the actual payloads agnostic to the kind of delivery formats. But very much speaking, we're still in that space, but in the end game here is an all compute processing, right from the glass to glass, from camera through to the consumption by the end viewer, wherever they are. And actually there are very few touch points that real-time video or audio is needed. But within this ecosystem, there is still, we believe, going to be a lot of need for various elements of compression as we actually work, even within a compute environment. So again, more on that a little bit to come. And just while we're just thinking about compute environments and cloud, I think I alluded to it just a few minutes ago, but as we go from ground to cloud, so as we uplink using whatever connectivity we're using to get into cloud infrastructure and back again, that necessitates some compression typically, maybe not lots of compression. And again, we're going to come back to that later. And also within the cloud. So more to come on those elements. Now, many of you will be very familiar with this. I'm not intending to unpack 2110. This isn't a talk on 2110, but I did just want to point out that one of the key, very useful elements of 2110, which I have to say, when we were in the drafting group and this was put forward as a proposition a couple of years ago, I was quite skeptical of, and that's the -22 compressed video container. It's kind of a generic wrapper that can be used for various types of compressed video. And whilst we were doing production within a campus environment, compression really typically is not needed, especially with the ever decreasing cost of interconnect and interfaces, more of which in a minute. But as we go long haul to interconnect, from that picture you saw, different locations geographically, then suddenly compression potentially is required specifically for the video. So the -22 is very important there. And again, we'll talk about that specifically in a minute. Now, as we look at the wide area connectivity, one observation that I've got is that the cost of both network interfacing and network bandwidth has been falling drastically. Thinking back to the days when you had your Sonnet or in Europe SDH systems, and 155 megabits per second was seen as like an unbelievable amount of real-time data connectivity. Well, we're now putting out 100 gig lambdas like there's no tomorrow for a lot of deployments in wide area networks. So bandwidth cost is falling, and certainly as an example in the UK, I was going to say football, but I need to call it soccer. Our Premier League soccer over here, we've got infrastructure at each of those grounds, and I think they're able to pull back 40 uncompressed HD feeds from each ground. And some of those could actually be very lightly compressed UHD as well, using 4:1 compression. But so that's 40 uncompressed 3 gig signals that you can bring back from each football ground, and it's cost viable to do that for that kind of tier 1 sports. Obviously, for other sports and other events, maybe having that number of uncompressed signals is not cost viable. But that cost is falling, and the interfaces are getting faster and faster. So typically, I think my assessment is at the moment within a campus, within a production environment, then typically, we're not now even considering compression, even though it was potentially being considered for UHD only a matter of probably months ago for some people. But certainly in wide area connectivity, especially internationally, if not nationally, then certainly compression is needed to make it cost effective. And just while we're talking about traversing the wide area network, just a reminder, we're not just talking about campus to campus, we're talking about maybe campus to cloud or OB truck to campus, the variety of scenarios. And again, just a little advert for a couple of bits of work going on, but it's not just the data we've got to handle, the media essences, but there's all the stuff about the control and discovery of all of those media flows, and how we make that ecosystem as plug and play as possible is also very important there. Okay, so why do we compress? What are the reasons? And this isn't supposed to be an exhaustive slide, it's just to make you think a little bit about what we're trying to achieve here. So if we think about storage, so we're not thinking about kind of specifically, we're talking about there are two reasons for, in a storage environment, why we might want to compress video. One is the sheer cost, to manage the sheer cost of storage, and the other one is the sheer scalability. You know, if any of you used to have one of those old MP3 players when you could choose your favorite 200 MP3 songs, and you could only really afford to encode them at 128 kilobits per second, or else you ran out of space. You know, as we scale up and we go to UHD and we go to high frame rate and high dynamic range, you know, we're creating insatiable amounts of more and more data. So storage is always a challenge, and there's a cost of storage. Can we afford to store them uncompressed, or do we do some kind of compression there, and the scalability of it as well. Then in the middle there, I just put in, I think it's becoming less of an issue, but certainly in some studio facilities, the cost of the interfacing has been seen as prohibitive over the last 3 years. So, you know, the cost of going from a 10 gig to a 25 gig interface, and, you know, has led some people to think about maybe they need some lightweight compression on UHD essences, even within a facility. I think we're moving away from that architecture now, largely speaking, or certainly for high grade production environments, but that has been a consideration. And then the bandwidth, as we actually network, the bandwidth cost and the bandwidth limitations. Now, bandwidth cost obviously is, you know, in some environments, it's just purely a cost challenge. Is it cost viable to give us the bandwidth? Obviously, there are some environments when we compress video, it's not just a cost. So if we're trying to get into people's homes using DSL technology, then there is a finite bandwidth that we really can't go above. So we're fighting for every last kilobit per second that we can compress to actually squeeze a number of HD flows or even UHD flows down someone's DSL link to their home. Similarly, if we're using a satellite for SNG or for sports contributions or something, or even just for the backups, you know, again, we're compressing because we can't go uncompressed there. So there are some bandwidth limitations in some areas, but bandwidth cost is typically the main issue if we're actually in a fiber-based service provided environment. Excuse me while I just take a drink. Now, a good friend of mine, I was talking to Matt Goldman about this last week, who's now lives over in the US. He used to work for ITV, the largest independent broadcaster in the UK, back last century, that is. And he once said to me, when we were actually analyzing the concatenation of compression systems in a broadcast chain, you only have one chance to make a first compression. And obviously that made an impression on me. But I just wanted to think about this, because as we think about compression, one of the things we have to think about is not just the compression we're doing at this moment in time within our distributed production environment, but the actual overall impact, because we know that there's going to be at least one more compression on the direct to home emission format, whatever that is, whether that's internet-based OTT or on demand, whatever, whether it's an offline file generation or it's a linear TV service, there's going to be compression involved then. Typically, it may be going to a storage, which involves compression, and there may be other elements along the way. I do remember talking to some friends at the BBC about sample rate conversion a few years ago and not concatenating sample rate conversion. And I think they worked out in the end that in one of their radio chains, they had 18 sample rate converters in the chain, even though a lot of them were even hidden on the front end or back end of digital devices that were actually part of that system. So concatenation of compression is important, and worth saying, just the prompt there on the screen, you know, you can get lossy and lossless compression, although most compression that we're actually really using for real is actually lossy to some degree, although we try and actually use it, the compression, at a level in the distributed production environment, in a level that has very, very minimal artifacts. Okay, many of you will be completely familiar with the concept of this triangle. I'm not gonna weigh on it, but as we look at compression, there is always a trade-off. There's a trade-off between the quality we want to achieve, the bandwidth which we're prepared to use, we can afford to use, and the latency. And again, latency, obviously, for emission stuff that Matt's going to be talking about next month is much less of an issue, because there's not really round trip involved. But when we're involved in a distributed production, then everything from the remote, if we're doing a full remote, the remote tally lights and PTZ stuff, right through, you know, everything is involved, as well as commentators and the human beings involved in the process. Everything, that round trip delays is very important. So latency plays a big issue there. So But we have expanded that. I'm going to unpack a little bit of this a little bit later on, but just so you can see, we've kind of expanded this triangle. It's some friends from one of our technology partners called Interpix that I largely stole this from. And what we're just trying to say here is there are different sweet spots for the different compressions. So as you can see, as we look at H.264, we can get much higher compression ratios there, but actually it compromises us on latency, it compromises us ourselves on the amount of compute that's needed to do it. And we'll come back to the choice there and the impact, but you can see for various levels of compression or no compression indeed with the uncompressed line there, then that's kind of an adapted look at the way compression works. So let's unpack just a few of these, and I'm not going to dive into too much detail on here, and I'm certainly going to leave the lower rail for Mr. Goldman to actually unpack next month. But we basically have in my book the red line, which is uncompressed. And as I said, there are many applications, certainly nationally now, where uncompressed video is what we're using, even long haul. We've then got mezzanine compression. Typically, mezzanine compression is fast compression because it doesn't involve actually having to do much buffering to actually make decisions and to do encodes or decodes. And then there's what I call temporal compression, which typically involves exploiting temporal redundancy as well as spatial redundancy in the images. We can obviously achieve much higher compression ratios there, maybe up to 100 to 1 on the original native uncompressed essence, but at the cost of some quality and some latency, etc., etc. So the two rows I've got here, the first row is a contenders in the mezzanine compression space, and the bottom row are contenders in the temporal compression space. And I'm aware there's some slight subtleties there and there's some nuances, and we can use some in others. But what I want to look at very briefly is predominantly the mezzanine compression, because in distributed production, generally we're trying to minimize latency, and generally the mezzanine compression, the more light compression, is typically affordable and definitely is obviously much lower latency, and we'll unpack that as we go. So the three contenders that we've been using a lot for remote production when we've needed to compress in recent times have been these three. There's JPEG 2000, so TRO1, the Emmy Award winning TRO1 was we finished in 2013. There was an uplift of that in 2018, which basically created ultra low latency, which if you think the way it's done is basically stripes. So you don't have to send the whole video frame before you can compress it. You can compress a stripe, send it, compress a stripe, send it, compress a stripe, send it. Several different technology compression uses that kind of approach. And JPEG XS, which is the last one on this list, which is the one that we've been actually majoring on recently, is actually an exemplar of that, because literally it uses many tiny stripes. So you only typically have to maybe cache 16 lines of video, and you then apply the wavelet transform, etc., to that, and you can be pushing that out, and then you get the next 16 lines of video, which means that we're very significantly below 1 millisecond as an end-to-end encode decode latency. So if you think of wide area networking, we're then actually in a very good place, because that's vastly less typically than the latencies you're going to incur in the actual transit. I guess to go across the whole US, you're probably talking about 20-25 milliseconds. So actually sub 1 millisecond for the compression decompression chain is negligible. So just one slide specifically on JPEG XS, seeing as that's the one we've been using. We actually deployed it for the first time on a large European project this time last year. So that's been exciting, and it's been very successful. It's very flexible. We're typically, I think, running it somewhere around 8:1 to be safe for that very pristine contribution, no perceivable degradation whatsoever environment, although it's actually flexible. You can take it up to 20:1 if you've just got some very relatively rough monitoring requirements. One of the key things about XS compared with JPEG 2000 is it's been designed bottom up to be optimal for implementation both on FPGA and GPU and CPU. So, and we've actually done implementations both on FPGA and CPU, so we can actually, actually witness to the fact that it's actually going to be good, is good in both those environments. So far more optimal for CPU implementation and GPU implementation than JPEG 2000. So that was a specific design criteria. Just coming back to that picture, because now that may give you a little bit more context. So if you look at the JPEG XS line in there, as you can see, it's actually low latency, it's low complexity. So actually we can instantiate a fair number of these both on FPGA or in CPU environments. We can get very high quality. Obviously, the compression ratio is the thing that's not as optimal, simply because it's not a temporal codec. But we've actually found that to be very, very useful and the ideal candidate. And there is a wrapper to map XS into -22. So if we're in our 2110 ecosystem, if we want to go long haul and actually send our video and audio essences long haul, then we can actually do that with -22, carrying XS in that payload. Two quick examples. This is the European example I talked to you about previously. So we're actually taking in at each of the locations, we're taking in uncompressed 2110-20, compressing it to 22, pushing it out over the wide area network, then decompressing it the other end. And the great thing, going back to that, you only have one chance to make a first compression. The great thing about it is this actually can concatenate very well with very, very minimal additional artifact. We also got into esports last November, last fall. Riot Games actually used JPEG XS solution to go internationally. Again, very low latency. So in the light of probably, I guess, roughly, we were talking, up almost 100 milliseconds worth of transit latency on this connection, maybe only 80, somewhere between 80 and 100 milliseconds it would have been. Then obviously 1 millisecond is absolutely negligible for the compression itself. So there are other compressions and other tools, and I put this slide up. I'm a big lover of NDI. I've been doing at-home church service production over the summer in COVID, using lots and lots of NDI. So it's got a very good application space, and I love it. But it's the elephant in the room, as I call it, and the other expression at the bottom, I don't know if you're familiar with it in the US, are horses for courses. Basically, I think NDI has a great application space within the compression it uses, which is basically a kind of an adaptation of MPEG-2. Again, it's an intra-only codec that they use to achieve low latency, and it does it again in bunches of 16 lines, so it achieves low latency, but it's really designed for a local subnet. So it's great for something where MDNS can work for your discovery, and you're within a little local production subnet on gigabit Ethernet infrastructure. So I think this has a good application, but it's not mainstream enough for us to use it for these long haul big applications. Now, another thing that's up and coming, and COVID has really accelerated this, is the use of other best efforts technology to actually get our signals even in a contribution world. So as I say, I've been doing at-home production, and we've been using any pieces of wet string we can on a Sunday to actually get signals from wherever we need to across our town. But we've been using lots of DSL, and obviously there's emerging 5G, as well as people obviously already using a lot of bonded LTE, bonded 4G infrastructure for carrying data. I put the picture of ISDN down there at the bottom because obviously ISDN was a nice deterministic. It was pretty low data rate, N times 64 kilobits per second, but it was a deterministic TDM data transport, whereas obviously everything we're talking about at the top there is packet-based and inherently best effort. So we're obviously incredibly bandwidth limited there, so we're typically using temporal compression. There's an NDI variant, which is temporary compression, which is basically a version of H.264. We're typically using a lot of H.264. And obviously alongside that, you obviously need to use ARQ technology such as RIST, a great new standard from VSF, or SRT or ZigZee as other equivalents there, or maybe not quite as equivalent. Spatial diversity, as in redundant paths, and FEC are all technologies that you need to use to battle the best efforts that you have doing that. I talked about XS, and we've actually been doing some tests doing it both in software in the cloud as well as on our virtuoso appliances on the ground, just to prove the ecosystem. And the great thing is, although this is a very latency unoptimized demo that I'm just putting up here that we did a few weeks ago, it actually shows, compared with using other forms of temporal compression, which are typically used for going to the cloud and back again, this actually gives us a great capability. Obviously, I went back and said previously that it's very important that we actually consider the control plane as well as the compressed data plane. So that's something that there's work going on. Little plug, there's 3 activity groups. I've talked about RIST already. There's 2 other activity groups happening in the Video Services Forum at the moment. One is on ground to cloud and cloud to ground and how we handle infrastructure within the cloud as well. And the other one is on how we actually take both the data plane and the control plane long haul, with or without compression, as we actually go through this contribution ecosystem. So as you'll see here at the edge of our facility, we actually want to do a whole load of different things, which may include compression of the video as we go from our LAN side, that green side on the left, to the WAN side on the red. We may want to compress and decompress our video essences as we go off and on there. I had a slide for it. I knew I did. I just didn't know where it got to. So that's just a plug for these 3 groups. Just a quick moment on timing as we draw to a close. Timing is very important. One of the 2110 systems, because obviously the challenge is once you start splitting a signal up, is how you bring it back together again. And many of you that obviously are familiar with SDI, you know, once you've actually embedded your audio and your ANC data, then you translate that SDI either as native SDI or as 2022-6, and actually it's always in sync because inherently you've done that. The risk, but the beauty of 2110 is you're splitting off all those individual essences, the individual audios or bouquets of audio, and the individual videos and ancillary data. It's very efficient to only route them to where they need to be to do the video processing or the audio processing, but obviously that means you need to reconcile them. Now, the great thing is within 2110 we did some definitions of timestamping. So we take PTP time, absolute time, we timestamp the RTP timestamps of the video and audio, and then we theoretically are able to then reconcile because we've got those timestamps. Now this is an appeal to the industry and to users that as people implement 2110, we've done some revisions recently to part of it to actually allow us to co-time our video, our compressed video or uncompressed video, along with our audio and other data flows, and to get people to honor the origination time, that original timestamp from the camera or the microphone A to D converter, as we propagate through the production process. That's very important. And that allows us at any point in the system to automatically reconcile time and realign the essences. And theoretically, it means you can even break apart phase coherent audio, stereos or 5.1s and reconcile them perfectly at the other end with these timestamps. So that's important, especially when you've got compression involved, which may actually introduce slight further elements of delay that you need to compensate with as well. So in summary, what I'm saying is we have an uber flexible production infrastructure now in this distributed production world where we've got IP LAN and IP WAN. Compression is actually quite important, especially for the wide area connectivity, typically mezzanine compression that gives us nice low latency. It can be part of the 2110 ecosystem, so we don't need to break out of our essence-based production environment that we've come to love and know in the last couple of years. And there's lots and lots of potential in terms of saving resources, real estate, processing, and people resources as we actually use this technology and as we actually have this full distributed production architecture. Okay, I think I've just about spoken for the 35 minutes I said I was going to. So without further ado, I'm just going to invite you, if you're ever allowed to come to the UK again, to come and see me, and I will make you a very nice cup of tea. So do reach out to me if you've got any questions or follow up that we don't answer in the next few minutes when Bob put some questions out. Then that's my cell number and that's my email address. I'd love to catch up with any of you and answer any questions I can. Hopefully that's been of some use. Any feedback appreciated. Thank you. Over to you, Bob.
That was so great. I'm going to start off asking you a few questions. First thing I was going to tell you is that I love the opening with uncompressed and fiber and everything on the bandwidth. I remember sitting on the transport panel at SVG, you remember, in New York, and them asking me about what do I see in the future. And my thing was that bandwidth's going to go up and the price is going to come down. And you're going to see more and more like that. And we have churches in Atlanta here that actually do uncompressed video between the campuses, which is just incredible. So that's great. The one thing I was going to ask you a question is that I was curious. Obviously, you talk about the JPEG XS. I was curious. What about TICO? I was excited at the beginning about it, and then XS came out. I don't like when I hear some people saying that TICO's dead, because I still feel like if there's a 3G infrastructure, fiber transport or something, it has a place. So what do you think about TICO?
Yeah, so first of all, TICO's great. We use it a lot and very specifically to address the issue you're talking about there. If we want to squeeze UHD into existing 3G infrastructure, it's an ideal candidate. And when I talked about the Premier League in the UK football, we've basically got uncompressed 3 gig infrastructure from all the stadiums. Mm-hmm. So if we're doing UHD from the stadiums, then we use 4:1 TICO compression to get the UHDs down to 3 gig to bring them in. A little bit of background on XS. So when the JPEG committee was developing XS, they actually looked at, I think, in the end, 5 candidate baseline technologies to build JPEG XS upon. And TICO was actually one of those 5 candidate technologies, and actually was the chosen candidate technology. So if you like, JPEG XS is an enhancement, an extrapolation, a building up of a baseline, which is a TICO compression infrastructure. TICO was really visually lossless up to 4:1, and that was really its limit for pristine visually lossless. Whereas JPEG XS, they've more than doubled that. You can approach 10:1 compression, but it's the same family of compression. It's the same concept. It's tiny stripes of wavelet compression. They did further work when they did XS. Not only on the compression, the actual compression ratio, the efficiency of the compression, they also did additional work on reducing the complexity for CPU and GPU implementation to make it multi-platform capable as well. But yeah, TICO absolutely still has a place. We're still using quite a lot of TICO solutions specifically to get UHD over existing 3G infrastructure.
Okay. And also then at IBC last year, if you remember, that's a show we used to go to.
Oh yeah, I remember shows when we used to meet up and all that stuff.
What I saw at Intupix is they were saying that, people were saying, hey, if you're at 10:1, can you squeeze it a little bit more and get us down, UHD down to just under a gig? And so I think they were showing UHD at like 875 megabits or something like that, which was really, really awesome.
Yeah, and I think it really depends what your threshold for truly visually lossless is. You can probably vary it. I think 10:1 is now is achievable. Depending on what bandwidth restrictions you have. Obviously, if you're trying to get below that 1 gig threshold, then you've got a finite bandwidth limit you're trying to work to. Mm-hmm. If you're in a more rich bandwidth environment, like typically we are for large scale deployments, where we're trying to do a decent compression, but we're not really pushing it, then for safety, I think we're typically maybe using 8:1 just to give some extra safety margin. But similarly, it's entirely possible to go 12:1 and reach that. I mean, certainly in a 50 hertz world, our video essence is only just over 1 gigabit per second anyway, so we can pull that down, and then correspondingly for the 10 gig as well for the UHD. Yeah.
Okay. And by the way, if anybody has any questions, please post them. I have one. I think I have one pending right now. Since I love when you brought up the slide about NDI, and I've been playing with it myself at home here, doing stuff. because we've had a lot of churches obviously ask about it, and then of course seeing the Brian's presentation on the NFL draft and how they were using NDI right from phones and all that stuff was very, very cool. But it's not a SMPTE standard. So do you think anything will happen there?
So as I say, I think it's horses for courses. I think NDI has a great application space. Obviously, the compression isn't pristine. It's a good compression. It's based on MPEG-2. It's relatively low bit rate, although it is VBR. If you've ever looked about how much bit rate NDI varies, it's quite astounding. It's a very good example of a VBR codec in action, because there aren't that many still in use that you see in linear worlds like that. I think it has this application space, but it's very much, in my mindset, NDI is great for small production environments that are sitting on a subnet. As soon as you want to break out of that, and if you want absolute tier one video quality, and you need routable infrastructure, and you need to scale and go cross locations, it doesn't really work in that world, but it does work brilliantly in that local production environment world. It's a bit like the analogy I think I use with some of the proprietary audio standards that have got a firm grip. They're very well optimized to work within a subnet within a campus environment.
Like Dante.
If you're trying to go long haul and you're trying to go off a subnet and route it, it has lots of challenges.
Exactly. Yep, I totally agree. Awesome. And then my last note was risk, but you already mentioned that. So anyways, all right, I have a question here. Thank you, Andy, for presentation. As more television productions crosses the international borders, are governments looking at taxing internet protocol payloads since they are now carrying intellectual property, i.e. television programming?
Wow, that's a great question. And that's a question I've never heard asked before. Certainly, I have not experienced that, even in what I would say some of the darkest places of the world. I've certainly experienced in the control systems that we've deployed on some international systems, we've actually had requirements where systems need to be able to continue to function within certain territories if those territories get isolated from the rest of the world, if I can put it subtly like that. But certainly I've not seen an interest or a requirement of any form of taxation there. There is some ongoing work that we're looking at in terms of encryption, and that actually is starting to, I think, raise its head more and more. I think traditionally in the broadcast world, when we've been using private wires provided by a trusted service provider in what I would call trusted territories, although which of those are now trusted, it's difficult to tell sometimes, isn't it? But within those, then actually encryption hasn't been seen as a mandate. Obviously, when we use OTT internet-based contribution, the work that RIST has done, etc., has obviously been making use of encryption because it's essential you encrypt when you're going over public internet. But we are starting to look at some of those encryption tools that have been developed and have been agreed on within RIST and applying them potentially to private wire infrastructure and also ground to cloud and cloud to ground infrastructure where we may well want to encrypt. Of course, you just need to make sure that the encryption isn't so aggressive that it can't cope with the kind of data rates, because a lot of encryption has been designed for relatively low bit rate use, and if we're running either uncompressed or only mezzanine compressed, then we're talking about very high data rate streams.
I remember Rick mentioned to me about with RIST about the you guys had some challenges with some countries with 256 AES compared to 128. All right, well, I don't see any more questions. I think we're good. Thank you so much. That was awesome.
Okay,
it was so
good to be with you.
We're we'll post the PDF of it on the SMPTE Atlanta website. Hopefully, whatever you can send me, whatever's approved.
Yep, absolutely, that's fine.
And we're looking forward to Matthew Goldman. He did join, by the way. He was on. So
if you're still there, hi Matt. Look forward to hearing you next month. I'll turn up for yours. I was going to make a Matt Goldman joke, but I can't think of one off the top of my head. I'll post it next month when he's talking.
Okay, all right. All right. Well, thank you, Andy, and thank you everybody for joining. And we'll see you next month on the 12th. So thank
Stay
you.
safe, and don't forget, if you're ever in the UK again, cup of tea. Call me.
Sounds great. All right. Thank you.
Take care.
Bye.
Cheers. Bye.